All right, great. So thank you very much to the organizers for inviting me. I guess I'm representing gravity for this workshop, so I apologize for that. So I'm going to tell you a little bit about some work that I did with my student Min Lee and some follow-up work. The goal is to understand a little bit better the connection between quantum error correction and gravity, more specifically ADS-CFT. So let me start there. I'm going to start with ADS-CFT and remind you a little bit what that's about. So ADS-CFT gives us a microscopic description of quantum gravity. It's a duality between some boundary theory that lives on the boundary of some spacetime, anti-de Sitter spacetime, which is pictured here. Some boundary theory, which is some CFT or some quantum field theory more generally. There are specific examples, the details of which won't really matter for us. And some bulk theory, some bulk quantum gravity theory that lives in asymptotically ADS spacetime, so it's not the quantum gravity theory that we experience. However, if we understand how this mechanism works, how gravity emerges from this boundary theory, then maybe we can say something more general. And so that's the general goal here, to have some picture of how gravity can emerge from some quantum mechanical degrees of freedom. There's two sort of important parameters in this duality that sort of map to each other. So there's g Newton in the gravitational side, and there's 1 over n in the boundary theory side. So 1 over n here, which is important in this talk, is you should think of as the number of degrees of freedom in the boundary theory. So that's like the number of fields in your quantum field theory. If you're thinking about some lattice theory, it would be sort of like the number of degrees of freedom on the site, right? So that's what we're taking. We're eventually going to want to take to be very large, so that g Newton is small. There's another parameter which is less discussed, which is related to some stringy effects in the bulk. So the quantum gravity is typically a string theory, so there's some scale associated to that, L string. There's a scale associated to anti-de Sitter space that I've set to 1, so that sort of sets dimensions here. And that gets related to some coupling, 1 over some coupling constant in the boundary theory. This is the 't Hooft coupling constant in n equals 4 super Yang-Mills. It sort of sets the size of the interactions. So in particular, we want lambda to be very big so that the string length is small, and that's where we expect to see sort of a quantum gravity that's more familiar to us. So we have these two parameters. Okay. So let me start then by giving a sort of a review of how people have tried to connect ADS-CFT to quantum error correction. And I'm going to do it by just giving you a toy model for what's going on. Okay. So I told you that ADS-CFT is this duality between some things that are going on in the bulk and some things that are going on in the boundary. So in these sort of toy model descriptions of that, we think of this duality between things in the bulk and the boundary as some kind of quantum error correcting code, where at least if you're trying to study some sector of ADS-CFT, you can think about starting with some state in the bulk, which will be sort of fed into these blue legs in this tensor network. And then you get some state out on the boundary, which is what the blue dots on the boundary. So we could pick any tensor network we like here. It's convenient to put it on hyperbolic space because that's like the time slice of ADS here. So here in this picture, time is going up. So there's various tensor networks that we could pick. You can think of this picture just simply like this, as some map between the bulk H, bulk Hilbert space that I'll call H, and the boundary Hilbert space K, or kappa. And this is meant to describe some state, for example, the vacuum, maybe of the CFT, and small excitations about that vacuum by sort of putting in different states, feeding in different states to this network. So I'm going to talk about a concrete example. So there's many examples, but let's talk about a concrete one. So I'm going to pick this network to be a random tensor network. So that means that at these vertices here, I sort of pick tensors that are randomly chosen. The tensors have, so there's sort of two kinds of tensors. There's in-plane, there are two kinds of legs that connect to this tensor. There's in-plane legs that have some bond dimension chi, and we're going to pick that to be very large. That's going to play some role like G Newton. Yeah.
Just a really naive question.
Yeah.
It's the space-time is ADS, right? It's not an ADS space just across time, is it?
No, yeah. So that's right. Yeah. So the time slice is, if you just fix time and you look at the metric on that time slice, it's hyperbolic space, but it's not equal to that times time.
Okay.
Yeah.
But I should take this toy example. I shouldn't think that it's a model for the whole space.
Yeah. So one issue with these toy models is dynamics. So we'll get to that. This is right now just describing the states, right? So some states in the Hilbert space, and maybe we can think about the entanglement structure, which I'll discuss now. Yeah. So okay, good. So we have this random tensor network of random tensors here. We have in-plane legs and we have out-of-plane legs. The out-of-plane legs are the things that are defining what the code is, right? So this is the code, the blue legs. And in this setting, you can show as long as the boundary dimension of the boundary Hilbert space is much bigger than the code Hilbert space, then this picture, this tensor network, becomes an approximate isometry. So V dagger V is the identity on H, which is the code subspace. And not only that, you can compute entropies of boundary regions. So if I pick a boundary region to be A, which is not drawn here, but A is this region here, I can try to compute its entropy. And typically, you get a formula which looks like the formula that you compute entropy with in ADS-CFT, which is called the Ryu-Taki-Nagi formula, where you just sort of minimize over the cut through this network, where you're partitioning the boundary vertices for A and A complement. So there's some minimal cut, and then the entropy is just related to that minimal cut times the log of the bond dimension of the legs that you're cutting. Okay, so this is very big. So this is like the dominant answer. But you can also compute some corrections, and the leading correction comes from a bulk entropy term of the quantum state that you're feeding into the network. So there's some state that I'm feeding in here, and I get the entropy. It's the von Neumann entropy associated to the bulk region little a, which is defined by the out-of-plane legs that are associated to the vertices here that define this minimal cut, right? So this minimal cut partitions the graph into two, and so yeah. And so this little a is called the entanglement wedge, and it has interesting properties, essentially because of this information theory, this information description of the entropy. So the Ryu-Taki-Nagi formula computes the entropy. It defines this region called the entanglement wedge, and the entropic aspects mean that you can actually do quantum error correction where there's a relation between little a and big A here. And similarly, this sort of situation is symmetric. There's a complementary region, the complement entanglement wedge AC, that's related to big AC, which is the complement over here. Okay, and so so we quickly get to quantum error correction. We think of V as some encoding map. The code subspace has some tensor product form like this. The boundary, the physical Hilbert space has some tensor product form like this. And essentially, as I said before, the quantum information in A is encoded in boundary region big A, and it's protected from erasure of the complement of AC. So if I just trace over AC, I can still extract the information in little a. By symmetry, we also expect the quantum information in A complement is protected from erasure of big A. Okay. This quantum error correction property can be seen in various ways, but there are sort of equivalent conditions to check whether this V here has this quantum error correcting property, and I want to focus on two of them. So these are equivalent. So if I have one of these, that implies the other, and vice versa. So the first one goes under the name of operator reconstruction. So it's the statement that if I have any operator that acts on this little a, then I can have a representation of that operator on this big A this representation is beta of phi a that acts, at least on the code subspace, like phi a. So V is defining the code subspace, so it acts like that. The other condition is this nil-Laflamme condition, where if I take the errors, right, so this is the thing I'm tracing over, so this is the errors. If I take operators in a complement, I project them to the code, they should commute with the code operators for this region little a. Okay. Now, often in quantum error correction, you're thinking about sort of correcting for everything in the code subspace, but this is a different kind of quantum error correction, sometimes called operator algebra quantum error correction, or subsystem quantum error correction, depending on who you talk to, where we're just correcting for some subsystem of the bulk of the code. Yeah. Good. Okay, so there any questions so far?
What is beta exactly?
Yeah, so beta is this representative. Yeah, I'll explain a little bit more. So it's a representative of the bulk operator in the boundary Hilbert space, in the physical Hilbert space. So the code, it's a representative of the code operator in the physical Hilbert space. Beta itself is a quantum channel, right? So it's a version of a quantum channel. So let me say that. So operator reconstruction uses this unital completely positive map on the algebra of observables. So it's a quantum channel in the Heisenberg picture. So you might be used to the Schrödinger picture where you have a CPTP map, but it's convenient for this talk to work in the Heisenberg picture. So the Schrödinger picture is just defined by instead of acting on the operators, you act on the states, and there's some equivalent. These are totally equivalent descriptions. Okay. And usually this beta, the dagger that you get using this operation is now acting on density matrices, is the recovery map that recovers the information in the quantum error correction code. In particular, we can write down the noisy channel. It's just encoding the code subspace and then tracing over the boundary region a complement. That's this erasure channel. This reconstruction condition is just equivalent to the fact that this recovery map takes some density matrix on the code, any density matrix on the code, and gives you back the density matrix in the little region A, in region A. Right? So you only recover the information in region A. Okay? And so this is the usual way of writing it. I'm going to write it like this in terms of this operator reconstruction, but I'm just telling you this is equivalent to this description. Okay? So now in this sort of specific random tensor network setup, we had this interesting setting where we had sort of a symmetric situation. We have what's sometimes called complementary recovery. So we can recover information in little a in the boundary region big A, or we can recover information in little a complement in the boundary region big A complement. And so we have sort of both, we have two conditions, right? We have one in this sort of equivalent condition here for little a and big A. We also have one prime, which is the same condition, but where I replace little a with a complement and so forth. Okay, so I make these replacements. So when we have this complementary recovery situation, you can prove there's a sort of a strong form of it where the relative entropy of the bulk states is preserved. So this is the relative entropy of the code states, I should say. I'm mixing my language a little bit. Hopefully that's okay. The relative entropy of any two code states is the same as the relative entropy in the physical Hilbert space, right? Where there's this relation between little a and big A. And you can show that this condition, if this is true for all states, is equivalent to this complementary recovery condition. And so here we can also see why the Ryu-Takinagi surface delineates this region. It's because you can show that the Ryu-Takinagi formula implies this equality of relative entropy, and so from that you sort of derive sort of quantum error correction from this RT surface. Okay, now some more comments. This is really only approximate in nature, so especially in this random tensor network case, the errors are controlled by the bond dimension. So this log chi you should think of as related to 1 over g Newton. And in particular, when this becomes large, then the errors get small. And what I told you is approximately true in some uniform sense, where we take sort of the operator norms. So for example, v dagger v is not really an isometry. It's only approximately an isometry. The reconstruction only approximately works. OK, and yeah, some other nice things to think about this example is if you sort of take a different tensor network where you just drill out and put some general state on these legs here, then you get a more general set of states in the boundary, in the physical Hilbert space, and you can think of these as black hole states that have swallowed up the quantum information. Now, this was a toy model. However, you can try to sort of just get this directly from ADS-CFT. And this was in the original paper where quantum error correction was introduced into ADS-CFT. And the essential idea was to take some states, or for example, the vacuum state, and act with operators that you can sort of reconstruct in the bulk easily using the full boundary, and then use that to construct a sort of very small code subspace. So we act with a finite number of bulk fields, and we build up a code in this way. And in this way, you expect a very similar behavior to the tensor network codes that we got, okay? That I was just describing. But let me some sort of point out some shortcomings. There's some question about how to pick these small subspaces. There's sort of many choices, like which one was the most natural. In this description, the things that we're acting on here are related to something called single trace fields, which I'll talk more about later. But what you need to know now is that there's sort of a collection of fields in the boundary theory that don't really form an algebra. And for this reason, I can't act with an arbitrary number of these operators, because if I do that, I'm adding more and more energy to the bulk. That will eventually collapse and form a black hole, and that's not good. So what you usually do is you act with some small number of operators, and then you do some projection, and that gives you some bulk algebra. But this projection then gives you some pause. It makes you question whether we can really precisely define locality in the bulk, and essentially, or locality in the code. That's what we really want to do. We want to understand how gravity is emerging in this limit, and gravity has locality properties in this sort of one extra dimensions, and we'd like to see them arise. And so maybe doing this, having these small finite dimensional codes, is bad for this purpose. The other issue is that dynamics is tricky. So there's no dynamics here. So to specify dynamics, I need to specify some Hamiltonian. But then there's some question about the bulk Hamiltonian versus the boundary Hamiltonian. How does that work? Apparently, Toby Cubitt will say something about this on Friday. So he has some non-trivial results here. There's other missing aspects of the bulk that you want. If you expected the bulk theory to be sort of small fluctuations about some geometry, that's a quantum field theory. It has causality, it has locality, it has things called energy conditions, which are related to causality and locality. We would love to see those arise directly from the boundary theory or the physical theory. And these sort of small code, quantum error correcting codes miss those aspects. And then there's another question which is related to sub-ADS locality. You expect, without doing anything else, that the code itself would be very stringy. So it is not going to be a local theory. So if I just took the n equals 4 super Yang-Mills with some coupling, which is order 1, which is not very large, but order 1, then that has a gravitational dual, which is really a string theory. And string theory is non-local on the string scale. And so it's natural to ask, does this fall into the framework of a quantum error correcting code? Okay. So I'm going to try to fix some of these issues. And the way that I'm going to do this is I'm going to enlarge this quantum error correcting paradigm to allow for quantum field theory Hilbert spaces in the bulk. So in the code subspace, I want this to be a Hilbert space that looks more like a quantum field theory Hilbert space. So what I mean by that is it's going to be an infinite dimensional Hilbert space. Okay, so now we're no longer talking about finite dimensional codes, which is something that you got in these random tensor networks, or by acting with these operators. We're talking about infinite dimensional Hilbert spaces. And we have to talk about now what could be entanglement wedges in the bulk. So we have these little A and this A complement regions. And because now we're talking about potentially quantum field theory in the bulk, we can't assume that the Hilbert space factorizes. It's a fact that in the continuum limit of a quantum field theory, the Hilbert space of a finite region does not factorize like this. The way to think about that is to think about the operators that act in this region. They form an algebra. That algebra is often conveniently taken to be a von Neumann algebra. So it's a sub-algebra of all possible algebras, all possible operators that act on the code Hilbert space. This is what's sort of replacing this tensor product here, where in the tensor product you would just have B of HA. That's all bounded operators on HA. That's a von Neumann algebra. But more generally, you have to just allow for some sub-algebra that doesn't take this tensor product form. It's a von Neumann algebra if it has some continuity property. So it's a closed set of operators in some topology. It's convenient. There's an algebraic description of that using this double commutant theorem, where if I take a collection of operators, I can always compute its commutant, which is just the set of all possible operators on B of H that commute with N of A. So that's convenient. That's an intuitive definition. If I take the double commutant and I get back to myself, that means that what you started with was a von Neumann algebra. Yes?
So just a clarification.
Yeah.
I think about this as the space, or this as space-time?
Good. You should think of this sort of as space-time, and I'm just drawing a time slice through.
I see. So it's kind of like a foliation of a quantum field theory. So
Yeah. So we'll get to that, but yeah, that's right. So anyway, so we have these subalgebras, and you can try to classify possible subalgebras that they could be, and there's this type classification of von Neumann algebras that's not super important for us. However, it is known that in quantum field theory, you get these type 3-1 von Neumann algebras, which do not have this tensor product form. You can't use density matrices. There's no traces on them, and there's all sorts of things you can't do. And the intuitive explanation for why that is that in any state in the quantum field theory, you always have this infinite entanglement near the edge of the region. Okay. Okay, so we want to sort of incorporate this into the quantum error correction paradigm.
just a question.
Yes.
Does type 2 never occur, or why not type 2?
Type 2 does occur. It doesn't occur in local quantum field theory. Yeah. We can talk more offline about why it's type 3-1.
So I thought, with background, you could get type 2.
Sorry?
With background, you could get type 2.
So in gravity, actually, there's a way to get type 2, not in the settings that I'm going to talk about, but yeah. Okay. So this, as part of this fix, I've made the code subspace infinite dimensional. But now we have to be very careful how we treat errors, right? So in particular, what I'm going to motivate is we're no longer looking for sort of uniformly approximate codes, where the error is sort of the uniform norm or the operator norm that I talked about before. But instead, we're going to talk about something called pointwise approximate. So that's one part of the fix. The other part is we're simultaneously going to incorporate the large n limit. So in some sense, previously we just had n as some fixed parameter. We imagined it was very big, or we had this bond dimension. We imagined it was very big. So to do that, what I'm going to imagine is I have actually this n parameter labeling some sequence of Hilbert spaces. So I have a sequence of physical theories, and I'm going to use H, that my code subspace is going to be the same for each n. So the code subspace is the same, but I have a sequence of physical theories. And so that means I have a sequence of encoding maps, these VNs that map between the code and the physical theory. As an example, this is not the example that we're going to think about, but as an example, you can just take this random tensor network example we gave before and make the in-plane legs vary in bond dimension, so they depend on chi n. And for each n, I pick a different random tensor network. It's random tensor, I can do that. But I hold the sort of the bulk, the out-of-plane legs fixed. Right? So the code's Hilbert space is the same, but the boundary physical Hilbert space is different. Yes?
Is it correct that the code becomes closer to approximate as n becomes large?
Yeah. So we'll see that, but it's in some very particular sense that I'll describe.
Sorry, I meant closer to exact, not closer.
Closer to exact, yes. So it's in some sense that it is in a limit, it's exact, right? So that, but we have to sort of say what we mean by that.
Could you also say briefly why you expect it to be approximate in the first place?
So there's various effects that give rise to the approximate nature. Quantum gravity has other saddles that you should include in the description, and they're often sort of non-perturbative effects, and they spoil this sort of simple picture of error correction. There's also just perturbative effects that spoil it. I think this is a feature that it's only approximate, and that's something that we should use. But yeah. Okay, so good. So now, to motivate this sort of new kind of picture of approximate codes, I'm going to prove a theorem, okay? So the theorem is a generalization of this theorem that I flashed before, which I didn't give a name, but is sometimes called information disturbance tradeoff, I think. So I'm going to call it that. So this is some kind of generalization of that. It's called the pointwise information disturbance tradeoff. So we're going to assume that we have these VN maps. I'm not going to assume much about them. I'm not going to assume they're isometries. But I will assume that they asymptotically become isometries. So in some limit, Vn dagger Vn is just the identity on the Hilbert space. Okay? And I'll say what limit I mean in a second. But under this condition, we can prove that the following are equivalent pertaining to some von Neumann algebras. Technically, we have to assume that they're hyperfinite. Ask me later why. But we take so it's pertaining to a sequence of von Neumann algebras, which are subalgebras of the physical Hilbert space, of this physical sequence, and some code von Neumann algebra. So you can show if you can reconstruct operators, you have some reconstruction map, beta n, that goes between this subalgebra n and the boundary algebra mn, such that asymptotically, in some limiting sense, they are reconstruction maps. So Bn acting on Vn is the same as Vn acting on n in some limiting sense. Then this condition is equivalent to this condition, which looks a little bit like the Néel-Laflamme condition, where I take errors. So the errors are in the commutant now of this Mn. And if I project them to the code, they commute with operators in n. Okay? So the claim is, the theorem is that these two things are equivalent. So we've sort of replaced errors with these sort of pointwise limiting errors. Now let me tell you what these limits are. So the weak operator limit of some sequence of operators xn going to 0 just means that if I take fixed states in the Hilbert space, in this case they're in H of xn, and I compute the matrix elements, then the matrix element limit to 0. And this is for all fixed states, right, in H. So this is the weak operator limit. And it's just telling you that matrix elements are limiting, right? So in infinite dimensions, this is not equivalent to the statement that xn in norm goes to 0. Right? So in particular, this may not be the case. So these are not equivalent. Of course, this implies this, but not the other way around. Okay? So this is the weak operator limit. We also used here the strong operator limit in this description. And the strong operator limit of some sequence just means if I fix my states like this and I compute the Hilbert space norm, this goes to 0. And this is for all psi, in this case in H.
So do you need this n to be a general algebra, or you can just focus on factors?
Yeah, so it's just an algebra. It doesn't have to be a factor. It does have to be hyperfinite, which is so far. Maybe there's a general proof in the general case, but this is the one that we proved. Yeah, that's it.
And the VNs are the coding maps in a way.
Yeah, that's right. Okay, so these limits are pointwise limits. They're pointwise because I fixed these things from the outset, right? I'm not allowed to take sequences of vectors. That's not equivalent, okay? So it's important that I fix them and I take the limit, okay? And so I think there's sort of physics going on here. So I think that's the next slide. No, sorry, I forgot. Yeah, so let me tell you another theorem that we proved. So we proved this theorem. And then we also proved a complementary version. So if we have reconstructions for this pair and for the commutant pair, when did we start again? 35. Yeah. So 20 minutes. Okay. If we have both of these things, well, these are actually equivalent. So having both of these things is equivalent to asymptotic equality of the relative entropy. That means I take the relative entropy of any two states in the code. I put them on the physical Hilbert space and compute their relative entropy. That's a sequence of relative entropies. If that limits to the code relative entropy in this algebra N, then that's asymptotic equality of the relative entropy. If that's true for all states in the code, then you can show this complementary recovery condition, and that's also equivalent to some condition on the modular operators, which I'm not going to talk about in lieu of time. Sorry. Okay. So, all right. So these are some theorems that motivate this work, and the relevance of Vn to ADS CFT is as follows. So I claim that we can derive a code that looks like this just by directly thinking about the large N limit of matrix-like models, such as SUN Yang-Mills theory, which is relevant for ADS CFT. This derivation is a little bit in quotes. We have to make a few assumptions, but it's quite a reasonable structure that arises. And so let me give you a sketch of the physics that arises from this. So this code Hilbert space is built out of single trace fields, which I will define in a little bit. As I said, at finite n, these operators don't form an algebra. If you act with enough of them, you might create a black hole. So they're sort of outside of the code. However, if you fix some state in this sort of Hilbert space built out of these single trace fields, then the microscopic description at some sufficiently large n will be well described by the code. And that's why it's sort of pointwise. We have to fix the state in the single trace Hilbert space at large enough n that will be well described by the code. Okay. So let me give you some details about how we derive this. And the idea is to follow sort of these recent works which were discussing how non-trivial von Neumann algebras can arise out of large n limits. And it's sort of doing that, but from an error correction point of view. So putting back in So let me go through some of this. So the idea is to think about something called large N factorization. So if we have some matrix like gauge theory, then typically we have sort of adjoint valued fields. And the single trace fields are just if I take a single trace and I take products of these matrix value fields. So these matrices are n by n matrices, okay? And so you get a bunch of these sort of single trace fields. And they will form some kind of sort of an algebra, but it's not quite an algebra. At large n, it becomes an algebra. At infinite n, it becomes an algebra. And so that's what you mean by these single trace fields. So the other thing we need is a sequence of states And so, for example, we might pick a sequence, the vacuum sequence of states. And the important thing is that these single trace fields have some smooth large N limit for correlation functions in that state. Right? So you get correlation functions of these single trace fields, and in the large N limit, they have some nice description. In particular, the correlation functions sort of factorize. They start to factorize because of this large N factorization. So, 4-point function can be written as a product of 2-point functions, up to sort of subtracting 1-point functions. So this behaves what's known as a generalized free field. If I think of this abstractly, phi I as the sort of n goes to infinity limit of these fields, then I get some kind of abstract C-star algebra, which is associated to these Wick contractions. So in particular, it's some kind of Weil or CCR algebra. But it's a very concrete thing you can write down. The limit of the sequence of states that we're working with then gives a state for this C-star algebra. Once you have a state on a C-star algebra, you can construct a Hilbert space using the GNS representation. So we get a Hilbert space. That's the Hilbert space of the code. Right, so along with this, we're going to define some maps that look something like this. They're not exactly like this, but in quotations, they look like this. They take the single trace fields, the formal single trace fields at infinite n, and they give us the representative of those single trace fields at finite n. That's kind of what we mean by single trace fields. They sort of a sequence of fields that exist at each n and allow us to take the large n limit. So we have these maps, and then we can use these maps to define a linear operator Vn in the following way. And modulo some assumptions on the convergence of correlation functions, you find these weak operator limits and these strong operator limits that I was discussing before. Gamma n then behaves a little bit like these reconstruction maps, beta n. It's not exactly a reconstruction map. It's not unitole completely positive. But it turns out it doesn't matter. You can still do a lot of things with them.
What's the lowercase n?
It's just an operator, yeah. So this is just an operator on this Hilbert space, right? So this is like the GNS representation. So there's some representation of the C-star algebra on that thing, and that's what n is. Yeah. Good. Okay. So good. So, that motivates this, but how about I sort of claim that we could give some picture of locality and dynamics? Okay, so how would we do this in the tensor network case? So we had some boundary lattice theory. We could just have a Hamiltonian for that lattice theory, and maybe it's local in some sense, and we can study dynamics for that Hamiltonian. Here we're in a situation where we're studying a CFT. The physical theory is a CFT. This is a relativistic theory, okay? So that means the Hamiltonian, there is a Hamiltonian for a CFT, but it has exact light cones. So that means that if I have some operator, so this is now time in this direction, and this is some fixed time slice here. If I have some operator to the future of this cut A, I can just sort of time evolve it back here, and it's exactly an operator that lives in this region, in this green region here, A. So instead of talking about the sort of operator algebra of operators living on these lattice sites here, which is some way you would build in locality in this sort of tensor network description, we end up talking about operator algebras associated to causal diamonds. Right? And that just comes from this relativistic light cones. So all operators in here can be written as operators on this time slice. So I may as well just talk about the operator algebra associated to the diamond. And so this is actually the context for algebraic quantum field theory, which is something that I snuck in there. Okay, so we're going to use algebraic quantum field theory. And the idea in algebraic quantum field theory is associated to these diamonds, you have von Neumann algebras. So these are von Neumann algebras. They're sub-algebras of all possible operators in the physical theory. Okay, good. So in fact, in general, there's just assignment. If you have any causal diamond, now this is time, and now this is a picture of sort of ADS CFT, the boundary theory at least. I'm just thinking about the boundary of this. So the CFT, it's natural to put on a cylinder that looks like this. And so now we have an assignment for each of these causal diamonds on the boundary, von Neumann algebra. Okay, and it sort of satisfies certain obvious consistency conditions, some slightly less obvious consistency conditions as well that I'm going to assume. So in particular, given a boundary diamond O, we can talk about the commutant diamond, which is the causal complement of O, right? So that's something we were doing before when we had A and A complement. This is the algebraic quantum field theory way of doing that. You have this diamond, and then all points that are space-like separated to O define O prime. And so we can talk about the operator algebra associated to O prime. And there's an important assumption we're going to make, which is Hague duality, which is the statement that sort of things are maximal. So the operator algebra associated to O prime is just the commutant of the operator algebra associated to O. There's nothing sort of in between here. On a lattice, this is a trivial statement. It's a little bit more subtle in quantum field theory, but it's a reasonable assumption. Okay. Okay, questions about this? Okay, so in particular, one thing that you find is with this sort of local understanding of what's going on, we can go back and look at these reconstruction maps that we found when we derived this code, and you find that these reconstruction maps localize. That means that if I have some, that means that there is a von Neumann algebra in the code Hilbert space that is generated by the single trace fields associated to single trace fields in the region O. So this is a boundary region. There's some von Neumann algebra. And these gamma n's become maps from that to the boundary region Mn of O. Right? So they sort of respect locality. Right? So they, and so together what I've introduced is some code which has sort of a lot of things going into it, but this is what we call an asymptotically isometric code. It's this encoding map along with these von Neumann algebras associated to boundary regions O and these sort of simple reconstruction maps, gamma n. So now let's talk a little bit about the interpretation of the C of O. So this C of O, you can show using the information disturbance tradeoff theorem that I proved. So one application of that theorem is to prove that these C of O satisfy the following property. So C of O prime, is some von Neumann algebra associated to O prime, is contained in C of O prime, right? So the commutant of C of O. And so I claim this is related to boundary theory causality. So in particular, this algebra, C of O, you should think of as related to something called the causal wedge in ADS-CFT. So now I'm going to assume ADS-CFT and draw a picture of what C of O is. In principle, we should derive, this thing should emerge from us, for us. And so in some sense, it has emerged for us, these C of O. This is the general description of the causal wedge. But now let me give you a picture in the actual ADS-CFT. So in ADS-CFT, we have this boundary region O, which is the green region. We can compute its causal completion in the bulk. And I claim that the von Neumann algebra of quantum fields in that region is this C of O. And one way to think about it is that it is a von Neumann algebra, so it should be associated to a causally complete region. And its causal completion with respect to the code Hilbert space. And the code Hilbert space is quantum fluctuations on some bulk spacetime, so it respects bulk causality. So that means you should get this sort of causal complete region in the bulk, and so you get this causal wedge. Now, one thing that typically happens for this causal wedge in general settings is that you can sort of compute it. It's some dynamical thing you can just compute. And you find that there's a gap. So in particular, if I have some boundary region O, I'm just drawing a time slice here. If I have some boundary region O and O prime, then C of O and C of O prime are not commutants of each other. They do satisfy this, which they had to, but they're not quite commutants of each other. So this is referred to as violation of Hague duality. And this is quite natural. In particular, these reconstruction maps are very simple. And so they're constrained by bulk causality. the interesting thing is if we can extend these reconstruction maps into this sort of no man's land here. And that extension defines what we mean by an entanglement wedge. So an entanglement wedge is if we can extend the reconstructions in the sense that I talked about reconstruction in this theorem to some region E of O and some complement region E of O prime. And those two things are maximal. So that means E of O prime is equal to E, the commutant of E of O. So if that maximal extension exists, then we call it an entanglement wedge. And you can prove various things about that extension. It's important that it may not exist. It just may not exist. The code might not give you entanglement wedges, right? In which case, maybe you think that the bulk is not a local theory or something like that. Okay, right, good. Okay, so.
Before you
Yeah.
move over, you say down there physically that corresponds to a no cloning theorem.
Yeah.
Can you maybe elaborate a little bit where I mean these regions correspond to infinite dimension to different tensor copies or blocks, I guess, right?
Yeah, you can think of it that way in the tensor network picture, sure.
Yeah, so but where's the no cloning theorem from?
Yeah, so what was I going to say here? I forget. So no cloning, yeah. So essentially no cloning you can think of as the statement that this entanglement wedge cannot leak into this entanglement wedge, because then I could sort of produce this quantum information on both boundary regions, and that would produce a cloning. So that's why this theorem sort of proves that if there's an entanglement wedge, it's unique and things like that. So you can't extend any further because that would violate no cloning. Yeah. Good. Yes.
Can you explain if the Hawk duality is broken?
Yeah.
What's the remaining operator do?
Yeah, I don't know. It's that thing. It's just some gap in the causal wedge. So in ADS-CFT, I know what it is. It's this thing here. But in a general code where I derived it from, it's just some gap. It's just some gap.
In the anionic literature, there's an approximate Hawk duality. I don't know it's right away. But
Yeah. So that's probably related to superselection sectors, and I'm sort of not worrying about superselection sectors in this. So there's probably an interesting story there where you think about charges, and it's related to charges in gravity, which is an interesting question. But not thinking about that. So Hawk duality is natural for me. Okay, so good. So all right, so I probably don't have much time left, but yeah. So let me say a little bit about vacuum codes. So the big question that's open here is whether we can give this sort of if we can find an entanglement wedge. If there is a maximal extension of these causal wedges which come naturally in these codes, is there an entanglement wedge? Is there a maximal extension? And so the next goal is to give examples where we can prove that there is a maximal extension. And so the first case is where we talk about vacuum codes. So that's this question. So a vacuum code. Well, so a CFT has a conformal symmetry by definition. The conformal symmetry is some group. It includes time translations along this cylinder that I drew. Okay, that's one of the generators. But in any case, there is some representation of this group on the boundary Hilbert space. So like a sequence of representations that holds fixed the vacuum state. The code itself may or may not furnish a representation of this symmetry. By definition, a vacuum code does. So that's what I mean by a vacuum code. It has a representation of this sort of conformal symmetry and some state that is held fixed by it. And in particular, these symmetries are covariant with respect to each other. So if I act with UN and then act with a code Vn, then it's the same as acting with Vn and then U of G, right? So it's sufficient to say this in some limiting sense, although it's quite natural this should be an exact statement, but it doesn't really matter. Okay, so in this case, for vacuum codes, you can prove for special boundary regions, in particular boundary regions that are diamonds, so they're the intersection of the past and future of a point, that defines a sort of a causal diamond. If it's a sort of very special boundary region that we want to consider, and you can show that the causal wedge it already is maximal. So that means Hugg duality is not violated for the causal wedge. That means the entanglement wedge is equal to the causal wedge. This result is kinematical. It essentially follows from the fact that the diamond itself is held fixed by a special conformal transformation, a special conformal boost. Knowing that allows you to prove this. Okay, I'm not going to go into details, but yeah. So there's some important steps there, but yeah. There's a more non-trivial. That's a kinematical statement. I'd like to try to make a more non-trivial statement. So here is the more non-trivial statement. Suppose that I know something about the partition function. Okay, so the partition function relates to the Hamiltonian. This Hamiltonian is sort of generating time translations on the cylinder. So we have that because we assumed we have this conformal symmetry. So we have that generator. And we ask if we take a limit of the partition function, do we get the bulk partition function? Okay, we may or may not get the bulk partition function, but let's suppose that we do. In particular, there's reasons to believe that if the temperature is lower than the Hawking-Page temperature, then in fact you do get this as a limiting statement. This Hawking-Page transition is just above some temperature, the ADS collapses and forms a black hole. Yeah, so but below that temperature it doesn't happen, and you get equality here. Knowing this, you can prove that for sufficiently separated diamonds, the entanglement wedge for two sort of disjoint diamonds is just the algebraic union of the causal wedges for those two diamonds. This is just all of the operators generated as a von Neumann algebra by the operators in each of these algebras. And so here's a picture of what's going on. We have diamonds that are separated in the bulk. If we did have ADS-CFT, we know the causal wedges are these sort of regions here. For a sufficiently large D, which means that the causal wedges are far enough away from each other, in particular this D is really the distance between the causal wedges, then our proof shows that the entanglement wedge is sort of additive. So it's just this is the correct picture for the entanglement wedge. This happens above this Hawking-Page temperature and how that relates to D here. Below that, we still expect it to be additive. Our proof doesn't work anymore. Okay, so we need to do a better proof here, but we don't know it. We expect at least for sufficiently above some D, we still have additive entanglement wedges. But if we go below some D, which is related to a transition where the entanglement wedge becomes non-trivial, so the entanglement wedge of these boundary regions becomes this sort of blue region here, then we no longer have additive entanglement wedges like this. So this is called the mutual information phase transition because the mutual information goes from order 1 here to order 1 over g Newton over here, so very big, or infinite really in our code. Okay, so we have this phase diagram as a function of D. There's another interesting point down here, which is related to something called the Hagedorn transition. So in particular, it's possible that our code is a string theory. And if our code is a string theory, then it has an exponential growth of states in its density of states. At large energy, the density of states goes exponentially with some coefficient given by this Hagedorn temperature. So this leads to a divergence in the partition function. So above that temperature, the partition function is just infinite. And in particular, this means that if I have causal wedges that are sufficiently close, D is sufficiently close, it's possible that you lose this interesting property called the split property, which tells you that the sort of algebraic union of these two diamonds is just the tensor product of the two diamonds. This need not be the case. There are this is something called the split property. It's not always the case. In local quantum field theory, we expect it's always the case. So this is now some way of distinguishing between codes that are stringy and codes that are not stringy. So in particular, I'll end on this conjecture. Local codes with some local gravitational description conjectured to have Hug dual extensions for entanglement wedges. And the causal wedges are always split. Okay, so let me finish there.